In the previous video, we met the idea of the particle zoo. In this video, we're going to look a bit closer at some of those particle properties about how we sort particles. There are certain things called quantum numbers. Quantum numbers are just numbers that we can use that have a particular value. And through some clever mathematics, we can give them nice, easy numbers to recognize, like 1, 2, and 3. But they correspond to discrete values. The easiest quantum numbers that you'll learn about are things like charge. So electrons have a charge of -1. Well, that's -1 elementary charge units, which is actually -1.602 times 10 to the -19 coulombs or something close to it. And you could then say, well, that's a useful quantum number because positrons have the same magnitude of charge, but it's the other sign. There are some other quantum numbers as well. And so we have this concept of a quantum state. A particle's quantum state is determined by its string of quantum numbers. And some of the quantum numbers that you might want to know about are things like the spin of the particle. You may know, for example, that you can get 2 electrons in the first shell of an atom. And you may think, well, why can I get 2 electrons in the first shell? Well, it's because those 2 electrons have opposite spins. So spin is a quantum number. But then in the next shell, you can get 8 electrons. And you may think, well, why can I get 8 electrons? Well, first of all, we can split that down the middle and say that you can get 4 electrons of one spin and 4 electrons of the other spin. But that's still 4 electrons in the same shell. Well, that's because the shell has a quantum number for its energy, and it also has quantum numbers for the angular momentum, which sometimes gets referred to as subshells. And you might see chemists talk about SPDF shells. Well, these are different quantum numbers for angular momentum. Now, you cannot get 2 electrons in the same quantum state. You just can't. They won't let you. But that quantum state can include many, many, many of these quantum numbers. And so you can end up with very exotic shapes of shells looking a bit like this. Particles that you cannot get into the same quantum state get called fermions, named after Enrico Fermi. But there are particles that you can get in the same quantum state. Particles such as photons. And actually, particles such as mesons that you can get into the same quantum state. And they get called bosons. Bosons named after Satyendra Bose. Now, these two use different sets of statistics to determine where particles are most likely to be. The statistics that govern fermions says that you can't get 2 fermions in the same quantum state. The statistics that govern bosons says you can. It's more subtle than that, and at university level you'll learn about spin taking on an integer number or a half integer number. If you have an integer, a whole number spin, then you are a boson. If you've got a half integer spin, 1.5, 2.5, 3.5, just a non-integer value, then you are a fermion. So our sorting picture looks like this, where we've got fermions that can't exist in the same quantum state, bosons that can. We've got particles like baryons and mesons that feel the strong nuclear force and are called hadrons or hadrons. And you've got leptons that don't feel the strong nuclear force, so they're not hadrons. These particles we always think of as matter. The particles on the right here, including things like virtual photons, get called the gauge bosons. They exchange forces. And 𝗟𝗶H thought that the pion was a gauge boson. Actually, the pion is a meson, and there's another gauge boson, but we'll come to that. And you can find various pictures where things have tried to be sorted to help you out in different ways. There are bosons that are hadrons, there are fermions that are hadrons. Hadron just means it feels the strong nuclear force. Fermion means you can't put 2 of the same particle in the same quantum state. Bosons means you can. Now, trying to put more than 100 particles into a table like this and sorting them out by their properties, it works, but it's a bit complicated. And it required the genius called 𝗟𝗶H𝗸𝘀 to figure out a way of breaking down that particle zoo of hundreds, maybe thousands of particles, down into very few particles and rules, simple rules for how those particles can interact. And that's what we're going to look at in the next video.